All right, we're going to take a moment to talk about how to create the ray diagrams for lenses. When we are drawing our lines for our light, remember that all of these lines are going to be straight lines. We are going to trace the path of two of our beams of light that come from the top of our object, and we're going to follow the rules that you see here on the screen. Step number 1 is to draw a line that goes from the top of our object, which is going to be an arrow in this case, straight into the lens and then through the focus. The second beam of light is going to just simply go straight through the center of the lens from the top of our object. So I wanted to take a moment before I go through the actual examples with you to give you some guidelines for knowing which focal point to use and what we are going to consider the positive and negative side for our focus and our image distance. So the first thing I want to point out is that on these diagrams, it's marked on the bottom one. I'm sorry, I don't know why it didn't show up on the top, but our focus or our focal point, that's the wrong one. Our focus or our focal point is going to be located at these two locations right here. Those are our focuses, our foci, and we are going to need to make a decision when it's time to create our drawings as to which side of the lens we're going to use that focus point from. Are we going to use the focal point that's on the same side as the object, or are we going to use the focal point that's on the opposite side of the lens from our object? So if we think back to just the generic information that we received in the previous lesson about lenses, we can go back and look. When we have a convex lens, this is going to cause the light to come through the lens and then converge on a central location on the other side. When we have a concave lens, this is going to cause the light to go through the lens and then spread out or diverge on the opposite side. So when we are trying to make our decisions about which focal point to use, we can simply recall what happens to our light as it passes through the lens, and that can logically just guide us through which focal point to use. So if I'm trying to create a ray diagram using the lens here up at the top of the page, I'm going to need my light to come straight into the lens. And then guys, whenever you make this drawing, you want that light to go to that vertical center line there on our lens. So from here, I need to decide, do I want it to go through the focal point over here on the left-hand side, so on the same side as my object, or do I want it to go through the focal point on the opposite side of the lens compared to my object? So we're definitely not going to draw it like this, but I just want you to see the difference between the two. One of those is going to cause the beam of light to be bent, so that refracted, so that it spreads out and away from the other light rays, and the other is going to cause it to be bent or refracted so that it comes in towards what will end up being a central position. So what is the rule? What is the expected behavior? Well, for this type of lens, we expect that light to come through and converge. So that means that we need this path to be the path that first beam that comes in from the very top of our object, that's the path that we need it to follow. So now that I know that, when it's time for me to perform step 2, I'm going to choose to use this focal point, okay? Now, if we think about our math, we said that we're using these formulas, which did not show up for us when I transferred it. So this is going to be 1 over F equals 1 over DI plus 1 over DO. And we got some ground rules for this when we learned mirrors, and we're going to use the same basic logic here. If the light is going to bend so that it converges, then we are going to have a positive value for our focus. If the light is going to bend so that it diverges, we're going to have a negative value for our focus. So when we look at our example diagram here, we want the light to converge. We've already established it's going to go through the focal point on the right-hand side, or on the focal point that is on the opposite side of the lens from our object. Another way to describe this is that it's the same side as the observer. So if I wanted to know where is my person standing that is looking at the light, my person is standing over here. So here is the perspective that the light will be received from. So if the light comes through the lens and then the focal point is on the same side as the eye, then we are going to call that our positive focus. So this is converging light rays, which means that we are going to have a focus that is a positive focus value. So when we say that we're using this focal point, this is the positive side of our diagram. Now, if we create an image that is formed over on this right-hand side, so if, oh, that was bad. If we create an image that comes together over here somewhere on the right, then we are going to also need to figure out what that distance to the image is, or find our DI. So when we do that, we have also identified some sort of rule or interpretation for positive and negative DI values. So if we look back at our notes, whenever we initially got our math, we said that a positive DI would be real and a negative DI would be virtual. Well, if we look at where our image is going to be located once we create our image is going to be located here. Here is my image. So this is going to be a positive value for my DI, because the same side as the eye is the positive side. And so positive DI means a real image was created, and that is indeed what we have here. Okay, now when we look at our diverging lens, so our concave lens down here at the bottom, we expect that our light that comes in to our concave lens, we expect that light to come in and then spread out, right? Looking back at our notes, that is indeed what we saw illustrated in these different examples we looked at last time. So we want our light to go straight into the lens, and once again, make sure you go straight into the center of that lens. And then from here, we need to once again determine which focus is the correct focal point. So if I have it go through the focus on the right-hand side, if I choose to use the positive focus, then that's going to cause my light to bend. And so when I do my second beam, it will have converged, right? If I do my bottom beam, it will converge into that same location. So that's not the focus that we want to use this time. This time we want to use the focus that is on the left-hand side of my lens, or perhaps we could say that's on the same side. And so this is the path that the light would travel. Again, we're not really going to draw it just like this, but this is the idea, okay? So we are going to choose to use the focus over here on the left-hand side. Now remember, we want our ruler to go through the focus so that we can see what that path should be for our light. We're going to use solid lines to draw our actual path of light, and then virtual lines to draw in any pathways that our brain is going to interpret for us. The second beam of light will go straight through the center of the lens. So when we look at our point of intersection, my image is going to form right here. That's a rough looking arrow. Let's try that again. So now I have a situation where my image is produced on the same side as my object. Once again, my observer is going to be over here on the right hand side. Here's the eye of the person that is looking at our image. So we are going to go back to what we learned with our math. If the light diverges, we want a negative value for our focus. So here is an example where the light diverged. So that means that this focal point is going to be the negative value of our focus. So diverging light is going to have a negative focus, and that is indeed what side of our lens we have our image created. So if we are looking at the same side as the object, that is going to be our negative side for our focus, as well as our distance to the image. So when we are identifying the meaning behind a positive DI or a negative DI, we say that negative DIs are virtual, and indeed we ended up needing virtual lines in order to produce this image, and this is the negative side for my lens. Okay, so DI and DF are negative. I'm sorry, DI and F are negative if it's on the same side as the object, and DI and F are positive if it's on the same side as the eye or the observer. Okay, so let's go ahead and look at some specific ray diagrams here. And I've already kind of gone through the instructions, so I'll do this rather quickly. The light is going to go straight into the lens and then through the focus. Do your best to make sure you hit that focal point. If you have to redraw it like I am, that is totally okay. We really want these drawings to be accurate. Sometimes figuring out where your pencil is actually going to touch the page is the tricky part. And then we want that second beam of light to go straight through the center of our lens. And the point of intersection is where our image is located. Okay, so this is going to be our image. This being our image is going to be smaller than the object, and I know this because the line for my image is shorter than the line for my object. Here's the length of my image. Here is the length of my object. It is indeed a shorter length. The image is going to be inverted because the point of intersection took place below that horizontal line, or what we call the principal axis. And then the image is real because I had real physical beams of light that met up, and we can see this in our diagram because we have solid lines. In this example, we have our first beam of light is going to go straight into the lens. And then we're going to choose the negative focus because this is supposed to make diverging light rays. We're going to draw the path that the light actually travels with solid lines, and then I am going to choose to go ahead and put that virtual line in because I know I'm going to need it. If you don't know ahead of time, no big deal. Draw your solid line, and you can always put that ruler back down on the page and add your extended dotted virtual line later. The second beam of light is going to simply go straight through the center of the lens. And again, that center is going to be where our horizontal principal axis meets our vertical axis. And I realize that my line is just slightly off, so I apologize. I would definitely be redrawing this if I were turning this in. And so here is my point of intersection, and so here is where my image is located. So my image is going to be smaller than the original object. I know this because the line for my image is shorter than the line for my object. The image is upright. I know this because the point of intersection is above the horizontal principal axis. And the image is virtual And how you want to word this, again, the purpose of this handout is for you to have instructions for yourself for future reference. So the image is virtual because the lines did not physically meet on their own initially, because I did not use solid lines to create my point of intersection, because I had to extend one of the lines in order to create a point of intersection, because my intersection included a dotted line. If you have one or more virtual beam of light, then we are going to call this a virtual image. So this is how we're going to create our drawings. Again, you are going to be expected to do some math work with this. So I am going to just kind of run through what the expectation is here for the math. I'm not going to do the actual numbers with you, but we're going to go through the process. So we have DI is going to be our unknown, because based off of what we have at the start of this handout, we can easily take our rulers and we can measure our DI and we can measure our we can measure our DO and we can measure our F. The DI is what was not already provided. So that would serve as our unknown in this case. So my DI will be calculated by taking 1 over F, and then I will subtract over 1 over DO. And then I need to remember that all of that must be inverted. So if you're doing this on paper, your numbers are going to be slightly different than if I were doing this here on my iPad. But remember, everything is being measured from the center of the mirror, okay? So my focal point here is going to be measured from the vertical line that splits my lens in half. And so let's pick a different color here so I can color code my picture. So my focus is going to be measured from the center of the lens to the focal point. Okay? This is going to be a positive F because it is on the positive side of our lens based off of the rules we established at the start of the lesson. So whatever I get this to be, it's going to be some positive number for my F. So 1 over, and I don't know what the measurement is for you on your paper. For me here on my iPad, it comes out to be 1.4 roughly. And we are going to keep this a 1.4. Okay, then it says minus, and now we need to figure out what the distance to our object is. So we are going to take our object and measure from the object to the center of the lens. So here is my DO, and remember your DO is always positive. So on paper, the measurement will be slightly different. On my iPad, this is going to be a measurement of about 5.5. And so I would then put this in my calculator, get that answer, and then invert it, okay? So when I perform this calculation, my DI is going to come out to be some sort of positive number. So whatever this number is, it's going to be some positive number. Now, how do I know that I should end up with a positive DI? Because my image is created on the positive side. So if I were measuring my DI, it would be from here to here. And remember, this side of the lens is going to be a positive distance, okay? So that means that my image, according to our rules from the day that we learned these equations, a positive DI means that it's a real image, and that is indeed what we calculated here. You will also be able to calculate the magnification. So I just want to remind you how that looks. It's negative DI divided by DO. So you are going to take whatever you calculated for your DI. So for me, this was a positive number. I'm going to put that in there, divided by our DO. And then in this case, I am going to get some negative value for my magnification, which means that I have an inverted image. Negative m means inverted. And then if I were to perform this calculation, I would end up with some decimal number. So decimals mean that my object is smaller. My image is smaller than my object, so it would be reduced in size. If we look here at the second lens diagram, once again, my formula is 1 over f equals 1 over di plus 1 over do. So my distance to the image is going to be 1 over my focus minus 1 over the distance to my object, and then we are going to invert that. So we are going to measure our focal length from the center of the lens to the focus. Now this time, this is the negative side for my f. So when I perform this measurement, I'm going to get a value of roughly 1.6, but I'm going to put it in my formula as a negative 1.6 because this is diverging light. It used the negative focal position. For the distance to my object, that is going to be, sorry, trying to keep my color coding the same for y'all. So the distance to my object is going to be measured from the center of the lens to my object. So there would be my DO, and remember that is always a positive value. So when I take my measurement, I'm going to use the value as is. So this comes out to be 1 over 5. So I'm going to put in my calculator 1 over negative 1.6 minus 1 over 5. And once I get that value, I'm then going to invert it. So my DI, in this case, is going to come out to be some sort of negative number. When you grab your calculator and punch that in, that's what you get. Now, if we look at my drawing, look at my ray diagram, and sorry my lines are overlapping here, it's getting crowded, but my object was here, so this is the length that I would measure for my DI, and that is also on the negative side for my ray diagram. So my picture does match the fact that my DI should come out to be some negative number. When we look at the interpretation of positive and negative DI, negative DIs are going to be virtual, and we did indeed create a virtual image on our ray diagram. Then if we look at our magnification equation, for this problem, don't forget it's negative of whatever you calculated. So it's going to be the negative of my negative number over my distance to my object. So for this calculation, I'm going to end up with some positive m value. And if we look at the meaning of a positive m, this means that my object is upright, which my arrow was pointing up just like the actual object. Once again, we do end up in this example with a decimal answer, and so decimal answers mean that my image